So having discussed the principle of virtual work, let's use it to determine the equilibrium condition of a common mechanical system. So as usual, we will start with our simplest example of a planar pendulum or a simple pendulum. So let's try to find out the condition for a planar pendulum to be in equilibrium under the effect of a horizontal force F. So we consider that this particular pendulum, okay, what I have shown in the diagram, it is in an equilibrium position, making an angle theta with a vertical. How can it happen? If there is a horizontal force acting on the bob along this direction, this pendulum can be in equilibrium at this angle theta. Okay. So if this is a static equilibrium condition under the action of an external force F, then we can find out its condition, find out the condition for static equilibrium by the principle of virtual work. So let's analyze the other forces acting on the bob as usual. Okay, so we are doing it so that we will get an idea about okay, what you call the Newtonian method also. Finally, we will try to compare the solution of the same problem by using Newtonian method. So let me say, okay, on this bob there will be some weight, okay, so which is mg, that is acting downwards. So mg is acting downwards, right? And see, actually there will be a tension in the string which will be acting along the pivot point, but I am not considering the tension here because tension is our force of constraint. The basic or the underlying aim of introducing the principle of virtual work is to get rid of the problems with the constraints, is to get rid of the use of constraints, okay, or the issues which is created by the presence of constraints. So it's actually a method to bypass, the calculation of constraint forces like tension and find out the condition for equilibrium. Okay, so I'm not considering the tension force here, even though that is also acting. Instead, I will be applying the principle of virtual work. So as usual, what we have to do, we have to imagine some virtual displacement and all. So let me just show the arc of the circle over which this particular pendulum can move. We say that this is the arc of the circle. Okay, so let's start with here. I'm making some modifications in the figure. So let me make a construction as usual. So let me say that this is some construction, this is 90 degree. Okay, so let me say the coordinates of this particular bob, let the coordinates be x and y. So let me say the coordinates of this bob be x and y. So I can say this distance is x. Okay, some OAB, we name it, so it is easy. So AB equal to x, and let me say OA is equal to y, and let this be the length L. Okay, so L be the length of the that is OB, that is the length of the string. Now from figure you can conclude that, right? So the pendulum, that's a issue, the pendulum, okay, is in equilibrium. This is the condition in static equilibrium, okay, in equilibrium under the force. It's a normal usual equilibrium should be somewhere here, right? That is a stable equilibrium position, but now it is in another equilibrium under the effect of, under the action of a horizontal force F, in the accompanying diagram. Okay, and what amount of force should be given, that's a question that we are going to address. Okay, so from figure, to do this one, let's say from figure from figure. Can you write expressions for x and y, which are nothing but the coordinates of the mass m? So let the mass be m be the mass. So the coordinates, what is x equal to? Can you express it in terms of the length L? Yeah, see, I can say x equal to L sine theta. Is that okay? X equal to L sine theta. That is the opposite side of the right angle triangle. So x equal to L sine theta. Okay, and what is y? Y is equal to, of course, L cos theta. X equal to L sine theta and y equal to what? L cos theta. Now here what you do, you imagine that this pendulum bob is given a virtual displacement. Here comes our technique. Let's imagine that the bob is undergoing a virtual displacement. You know, the virtual displacement should be consistent with the constraints, means it can either move this way by a small amount, or you can imagine the bob to be moving in this way along the arc of the circle by very small or infinitesimal amounts. Okay, so whatever direction it is moving, whether it is towards the equilibrium position E or away from the equilibrium position E along the arc of the circle, it will cause a small change in the coordinates x and y. So let me call the changes in x and y as the virtual displacement, the component of the virtual displacement along x direction and the component of the virtual displacement along y direction. So I'm calling delta x as the virtual displacement, okay, along x direction, and delta y be the virtual displacement along what? Y direction. Or these are the virtual displacements in the x and y coordinates due to a small virtual displacement delta theta following the constraints. So what you can do is that you can imagine that this particular bob has been moved a little bit like this, so that there comes an angle here, and this angle is what? Delta theta. Okay, so what I can do is that if the pendulum, or if the bob, if the pendulum undergoes, so of course this is imaginary, it's not a real displacement, undergoes a virtual displacement, which is an instantaneous displacement or imaginary displacement, okay, such that this angle theta is changed to theta plus or minus delta theta, or just you write theta plus delta theta, where the delta theta can be either increasing the theta or decreasing the theta, right? So theta is changed by theta plus or minus delta theta. So delta theta is the virtual displacement here, angular displacement. Then correspondingly, what will happen? So this is equation number 1. Let me call. Therefore, won't there be a change in this x and y? So let me calculate that by differential changes. Okay. So the same mathematical technique we are applying. So I can say from equation number 1, I can say delta x. So it's just like taking differential delta x. So what will be delta x is equal to, L is a constant. Okay, taking differentials on both sides, like you are taking dx. So L is a constant, so it will become L is written as L. So what will be the differential of sine theta? So that will be what? Cos theta. Now you have to take what? Because it's theta which is changing, function root. So I can write L cos theta delta theta. Right? L cos theta delta theta. And what will be delta y? Variation in y or change in y, delta y. That will be equal to, similarly L is constant, and you take a differential of cos theta. What will be that? Minus sine theta, right? So I can write minus L sine theta and delta theta. Minus L sine theta delta theta. We are taking total differentials. So that is my equation number 2. Now we are applying the principle of virtual work. What does it mean? Okay, the total virtual work done by the external forces should vanish for the system to be at what? Equilibrium. So since system is in equilibrium, we are using it in the counter way. Okay, static equilibrium, the total virtual work, total virtual work by external forces. That's important. External forces. Already the constraint forces are assumed to be doing zero work. External forces should vanish. That's the argument, should vanish. here is where we apply the principle of virtual work. So what does it mean? What are the external forces other than the see what you call tension, which is a constraint force? They are F, which is the horizontal force we are applying, and mg, which is the vertical force due to gravitation. Okay, so what I can write is I can calculate the total virtual work by the two external forces. Okay, what is that? I can do it individually. I am writing F, okay, F along x direction, F along x direction into displacement along x direction, that is what delta x, right? Okay, plus force along y direction, only these two forces are there, no? Into displacement along what? Virtual displacement along what? Y direction. So these two things should be adding up to give you 0, right? So since they are in the same direction, okay, just what I'm doing is that I'm taking that. So what I should do is that fx delta x plus fy delta y should be equal to 0. What is this one? Fx is nothing but force along x direction is having magnitude f. So I can write this is nothing but f into, which is the horizontal force magnitude, into delta x. What is delta x? Delta x is L cos theta delta theta. L cos theta delta theta. Plus what is fy? Fy is nothing but mg. Sorry, I can write fy as what? Mg. Fy is nothing but mg. Reason you can clearly understand, because that is a force along y direction, vertically downward. Okay, so mg into, right, what is delta y? Delta y obtained from equation number 2, that is minus L, that is a virtual displacement, L sin theta delta theta, that is should be equal to what? 0. Can't you just rearrange the terms here? Okay, so on rearrange the terms, what will happen? This okay, L and L will get cancelled, of course. So let me write it for the time being. So therefore I can write F is equal to, or F into L cos theta delta theta is equal to, you take this term to the other side to become plus, so it will be mgl sin theta delta theta. So can't you cancel away the things? You could have done it otherwise also. Okay, so this L and this L should get cancelled. So what you are finally left with, F equal to, I need the condition for equilibrium. So F equal to, simply you take that cos theta to the other side, it will become mg, right? Sin theta by cos theta is what? Tan theta. Mg tan theta. Okay, F equal to mg tan theta. It means that this is the condition, which is nothing but the condition for static equilibrium under a horizontal force F, static equilibrium. Okay, it means that if we are able to provide a horizontal force of magnitude F equal to weight mg times what? Tan of the angle of inclination theta, angle of the pendulum theta with the vertical, then you can maintain the bob at that angle statically. Okay, so if you have to increase, you can just always check the logical correctness of this equation. If you have to maintain a static equilibrium at a greater angle theta, okay, then tan theta will increase. So to do that, you have to apply more force. Okay, I think it is clear. It's just like, you are hanging something and you are blowing some air. If you blow strongly, can't you keep that object to be hung in a different direction? It's just like, some objects, hanging objects are chandeliers and all. Some hanging objects are carried away by the wind, and if the wind is steady, can't you see that the object is just keeping at an angle in a stable equilibrium? So if you are able to give a horizontal force to a hanging object, that object can be kept in a particular angular static equilibrium, okay, which depends on the mass as well. So that is the condition. Now you may not feel this result as exciting unless you do it by our ordinary method of Newtonian mechanics. So I will quickly complete this result. Okay, I'll quickly obtain the same result F equal to mg tan theta, the condition for static equilibrium, by using our Newtonian method. Okay, and just compare the two methods and see what actually is the difference of virtual work method. Okay, so let me do that quickly. See, since we are very familiar with the method of Newton, it won't take much time for us. Okay, so all the assumptions remain the same. So just not drawing much of the things. Okay, so because we know we need not do much, because Newtonian method is so familiar for us. So in the Newtonian method, you know what we have to do is that you have to find out all the different forces acting on the system, all forces acting on the system, that is to be known, because we are doing by the free body diagram technique. So there's only one mass m, so there is only one free body. I can draw it here. So what are the forces? We already seen the force mg acting vertically downward. So this is mg as usual. Okay, so this angle is assumed to be theta. This is some L. Okay, all those things remain the same, nothing. And we have assumed that there is a horizontal force F. Okay, one more thing, in our virtual work problem we neglected the tension because it was a force of constraint. Our aim was to bypass including the force of constraint. Okay, so we neglected the force of tension there, and we just imagined virtual displacement which was consistent with this force of constraint without affecting the tension, right? Okay, you know that if displacements were large enough, if it were not infinitesimal, then it would have affected even the tension, because you know the tension of the string is different at different places. It changes with position to position in the case of a pendulum, right? Tension varies. That is one reason why we are imagining only infinitesimal displacements which do not violate what? The force of constraints considerably. Okay, now see, I'm taking tension which is away from the thing. Now can't you do one thing? Can't you resolve the tension along x and y directions? You can resolve the tension along x and y direction. That is a method that we are doing usually, So let me do the resolution here. The tension T can be resolved like this: one along the y direction and other along what? The x direction. See, this is what I don't know whether it is visible to you. Let me use another color. That's better. Okay, of course. See, I'm resolving the tension. Let this be the tension here. So I'm resolving the tension one like this. Okay, of course, the length of the arrows I'm not able to maintain now. Okay, see, it should be something higher, no? Because this one should be something like so it should be a rectangle. Okay, see that my arrows are not matching, but be careful about it. I didn't plan it well. Yeah, of course. Then all these arrows should be different. Okay, yes. Just think about its directions only now. So let me say that I have resolved the tension. Let this be the tension here, from here to here. Let that be the magnitude of the tension represented by the thing. So the tension is resolved. So if this is theta, of course, if this is theta, then you can just know this is also theta. Okay, so this will be t cos theta, and this one should be what? T sin theta. Is it not? That is our role. T cos theta and T sin theta are the components of the tension along x and y direction. Now for static equilibrium or for equilibrium, what is the condition? The force along x should be balanced and the force along y should be balanced. So what is the force along x direction? Along x direction, you are getting F is equal to T sin theta. Is it not? That's a condition for equilibrium in Newtonian method. Force along x direction should be balanced and force along y direction should be balanced. And what is the condition along the other direction? That is mg is equal to, along y direction, mg is equal to what? T cos theta, right? Mg equal to T cos theta. So this mg should be balanced by this T cos theta, and this T sin theta should be balanced by what? The horizontal force F. So they should be balanced along x and y direction separately. So now you know what to do, right? I don't need the tension. I am not interested in knowing the tension. So see, this is 1 and this is what? 2. You divide 1 by 2. What does it give you? You will get F divided by mg. That is equal to T, and T will be getting cancelled. Sin theta by cos theta is what? Tan theta. Okay. And our aim is to get what force is needed. So F equal to what? Simply mg tan theta. Okay. Just look back. In very few steps, you have got the result what you needed and what you obtained by the principle of virtual work, which was new to us. See, F equal to mg tan theta, same result we have obtained. Maybe you feel that the method of virtual work is lengthier or complicated than the Newtonian method. Okay, of course in this particular problem it happens so, but you will see that by applying the principle of virtual work with more practice, okay, you can bypass the calculation of constraint forces. Okay, so in simple problems maybe Newtonian method is quite easy and straightforward, but in pretty complicated problems, okay, I have given some examples in the previous video, like equilibrium of trusses. These are something, equilibrium of trusses, truss, okay, those complicated structures that you construct over buildings as roof. Okay, you know, they are supported by a number of, okay, let's note connections between pillars and all those rods, right? Okay, so construction of bridges means mainly civil constructions. Okay, like towers, yeah, that's an okay, like mobile towers, you know, the construction is so complicated, and the all those parts of the tower should be so connected between them that they all make a very stable structure which is able to withstand what? Powerful winds. The Eiffel Tower, you think of, okay, such a huge structure which is able to withstand all those hurricanes, all those okay, cyclones. You know how strongly it should be designed. So all those different parts of that tower should be so positioned. Okay, the angles matter, the distances matter, all those things matter, the strength of material matter. Okay, so it should be so well designed such that the entire system should be finally in static equilibrium. It is not affected by, okay, any of the disturbances. So how it is done? It is done on pen and paper, using pen and paper, by imagining what are the possible swingings, okay, what are things can happen, what happens if one particular thing is just tilted this way by this much angle. Okay, so they are all imagined. Virtual displacements were given to each part of the, okay, it can be done. This is one of the method. We imagine virtual displacement to be given to each portion of the, okay, structure, then how it will affect the other part, okay, how to cancel it away, all those things. So the condition for equilibrium of those complicated structures involved, which includes what a lot of constraint forces, can be okay, calculated or designed by the principle of virtual work. So the principle of virtual work is of use in solving complicated problems with a large system where there are a large number of constraints involved. Okay, where of course the Newtonian method will be of no use, because when there are large number of constraints involved, of course solving the problem by resolving the tension along different direction and all will be quite difficult. It will be a tedious process. Okay, and especially when there are large number of degrees of freedom. Okay, there the concept of degrees of freedom becomes very important. Whenever there are large number of degrees of freedom, applying the Newtonian method will be quite cumbersome. It will be quite difficult, especially when there are a large number of constraints involved. Okay, that is why we are doing the method of virtual work, which will finally give you an idea about another principle, fundamental principle in analytical mechanics known as what? The D'Alembert's principle, which will take you near to the Lagrange equation of motion, the soul of Lagrangian formulation. Okay, so hope you understood what's the principle, what's the concept of virtual work. Please read more on this one. I don't I don't expect that you have got the complete concept